Hello, everyone. My name is Roy Lewis. Before I start, I want to thank Jessica Barth and her colleagues at the University of Delaware Multimedia Center for help in making this video presentation. The title of my presentation is The Riemann Hypothesis, an idea whose time has come. I borrowed part of this title from the title of an essay by the late pastor Harry Fosdick titled, To be Used by an Idea Whose Time Had Come. Pastor Fosdick's theory was that when an idea's time has come, it often chooses a person no one would expect to bring it forth to the world. This presentation is based on an article I published in 2022 in the journal International Mathematical Forum with the title, A Formula for Merton's Function and Its Applications. The article also is available on the HAL and Vixtra archives. What I hope to do in this video is to share the results of the above article with a broader audience in a short presentation that is interesting and understandable. So I will not be discussing all the details of the article, but try to present the basic ideas behind the article to help viewers who choose to read the original article understand the line of reasoning. The Riemann hypothesis, or RH, as sometimes referred to as, is stated as a function of a complex variable S in the complex plane. It states all the non-trivial zeros S equals sigma plus IT of the zeta function zeta of S have real part sigma equal to 1/2. The Riemann zeta function is defined on the complex plane by the following simple-looking but very complicated infinite series of the sum of the reciprocals of the integers raised to the power S. Number theorists have great interest in Riemann's hypothesis because of its relationship to the error in Gauss's formula for the function pi of x, the number of primes less than x, given by the integral in the second equation on this slide. This is the prime number theorem, or PNT. Von Koch proved if Riemann's hypothesis is true, the error in Gauss's formula is less than a constant times log of x squared divided by the square root of x. For large numbers, this is a very small error. I will be using a limit form of the prime number theorem shown in the equation at the bottom of the slide. Pi of x times log x divided by x equals 1 as x tends to infinity. In this presentation, I will examine Merton's function and its relation to Riemann's hypothesis. The Merton's function, which we write as m of x, is a complicated function because it is divided in terms of, or defined in terms of another function called the Mobius function, mu of x. For a positive number x, Merton's function, m of x, is defined by the sum m of x equals mu of 1 plus mu of 2 plus mu of 3, and so on to mu of n, where n is an integer less than or equal to x. In this equation, mu is the Mobius function, and the numbers in parentheses following mu are all of the integers less than or equal to x. On this same slide, we show how mu of n is defined based on the number of prime factors in the number n contains. Mu of n equals 0 if n contains a square of a prime. Mu of n equals plus 1 if n equals 1. Mu of n also equals plus 1 if n is square free with an even number of primes. Finally, mu of n equals minus 1 if n is square free with an odd number of primes. Let's consider a simple example such as m of 9. To compute m of 9 directly from its definition, we would sum the mu values of each integer 1 through 9. And to compute these mu values, one needs to determine the prime factorization of each integer, as I have shown in this example. For small numbers, computing these terms is easy. But for very large numbers, such computations are not possible, maybe until we have quantum computers. So, for the number 9, after adding the plus ones and minus ones and ignoring the zeros, we get m of 9 equals minus 2. You may have observed mu of 5 and mu of 7 are highlighted in bold text. I will explain why shortly. Using the example m of 9, I want to make some observations that form the basis for deriving the new limit equation in the published article. Based on the definition of mu, we don't count mu of any even or odd integer that contains a square of a prime as a factor, because their mu values equal 0. So in our example, we can ignore the integers 4, 8, and 9. Based on the structure of a square-free integer, we can identify many other integers whose mu values we can ignore. For example, every even square-free integer contains the prime 2 multiplied by one or more distinct odd primes, except the prime 2 itself is multiplied by the number 1. Therefore, for every even square free integer less than or equal to some number x, there must exist an odd square free integer less than or equal to x divided by 2, whose mu value is the opposite of that of the even integer because it contains one less prime factor. So they cancel out each other exactly. We see in our example, mu of 6 is canceled by mu of 3, and mu of 2 is canceled by mu of 1. What this implies is, to calculate m of x, we need to compute mu values only of odd square free integers greater than x divided by 2. This relationship is lemma 1 in the published article. Therefore, in our example, to compute m of 9, we need only compute mu of 5 plus mu of 7, which equals minus 2. That is why I had them highlighted in bold. Next, I want to discuss the subtle connection between the basic arithmetic operations of addition and division and the prime counting function pi of x to Merton's function. These are the mathematical tools used to prove Theorem 3 of the article. An alternative way to compute m of x is to count the odd square free integers greater than x divided by 2 in groups. For example, one could multiply the number of odd square free integers having an odd number of primes by mu of n equals minus 1, and multiply the number of these integers having an even number of primes by mu of n equals plus 1, and add these numbers. In the article, I do this by generating odd square free integers in the order of their odd square free divisors, like 1, 3, 5, 7, and so on. For example, the square free numbers greater than x divided by 2 and divisible only by 1 are the primes. We can compute this number by taking the difference between the total number of primes less than or equal to x, which equals pi of x, and the total number of primes less than or equal to x divided by 2, which equals pi of x divided by 2. Multiplying this difference by the mu values of primes of minus 1 gives the first term for m of x, shown on this slide 6. So, conceptually, it is easy to compute the contribution of primes to m of x. But in practice, it is not possible for astronomical values of x. The same can be said for composite square free integers. Now, let me explain how to use the prime counting function to count the number of odd square-free composite integers less than or equal to x. It is obvious that in square-free composite integers, all of the prime divisors occur only once. Also, rewrite their prime factors in the order from smallest prime to largest prime. This helps to keep track of the counting process. For example, rewrite 21, which equals 3 times 7, as P2, P4, or P2 dot P4, because 3 is the second prime and 7 is the fourth prime. And we write an arbitrary odd square-free integer as P sub I triple dot, which represents a square-free integer containing either one odd prime, like 3, 5, 7, and so on, or the product of two or more distinct odd primes, of which P sub I is the smallest. This symbol, P sub I, makes writing the terms in the infinite series we will develop simpler and less confusing. Next, I'm going to show how to generate and count odd square-free composite integers less than or equal to a number x greater than 4. We start by recalling some tricky but simple facts. Stop. Shit. For a number x, any composite square-free integer less than or equal to x must contain at least one prime divisor less than the square root of x, because if it had no prime divisor less than the square root of x, the product of any two of its prime divisors would be greater than x. Also, it cannot have more than one prime divisor greater than the square root of x, because if it did, the product of two of those primes would be greater than x. These facts imply that to generate odd square-free composite integers less than or equal to x, we only need to find the complementary prime divisors of their square-free divisors composed of primes less than the square root of x. Let's examine the arithmetic operation of division more closely. For example, what is 15 divided by 3? The answer, of course, is 5. But what does this number 5 mean or represent? One obvious answer is it means if we add the number 3 to itself 5 times, or multiply 3 by 5, the result will equal 15. Okay, perfect. But another meaning of the answer 5 is that there are 5 multiples of 3 less than or equal to 15. Because if 5 is a multiple of 3 less than or equal to 15, certainly the multiples of 4, 3, 2, and 1 are also less than or equal to 15. So the multiples are 1 times 3, 2 times 3, 3 times 3, 4 times 3, and 5 times 3. The problem we face next is how to find which of these multiples are square-free and odd. To solve this problem, the insight I had, or that was given to me, was to use the prime counting function pi of x a second time. So, if we take pi of 15 divided by 3, we get pi of 5, which equals 3. So, there are 3 prime multiples of 3 less than or equal to 15. They are the primes 2, 3, and 5. But now we have other problems. 2 times 3 equals 6 is square-free, but it is even. And 3 times 3 equals 9 is not square-free. These are problems because, remember, we only want to count odd square-free numbers. At this point, I thought these obstacles would mean the end for this approach. But after some weeks, another idea popped into my mind on how to fix these issues. The solution to these issues that came to mind was to simply subtract out the primes less than or equal to the primes in the square-free divisor, which is done by subtracting pi of the largest prime of the divisor. So for the number 15, we would get the term pi of 15 divided by 3 minus pi of 3 equals 3 minus 2 equals 1. Therefore, for the number 15, there's only one odd square-free multiple of 3 containing a divisor greater than 3, and that is 15 itself, which equals 3 times 5. So we resolve this issue. However, we're not finished because our methodology requires us to compute the difference between the number of odd square-free multiples of 3 less than 15 and those multiples less than 15 divided by 2. It turns out that for finite values of x, like 15, it is possible that x divided by 2 may not have any square-free odd multiples of a prime p sub I that are greater than p sub I and less than x divided by 2. In such cases, pi of x divided by 2 divided by p sub I minus pi of p sub I equals 0 or is negative. Let's assume that x divided by 2 is sufficiently large, such as when x tends to infinity, so that for some prime p sub I, the term pi of x over 2 divided by p sub I minus pi of p sub I is greater than 0. Then, to calculate the number of square-free multiples of p sub I between x divided by 2 and x, we use the next equation. After performing the subtraction and canceling the pi of p sub I terms, we obtain this last equation on the slide. Pi of x divided by p sub I minus pi of x divided by 2p sub I. The same issues apply to finding the number of odd square-free multiples of divisors containing 2 or more primes. When x tends to infinity, here's the expression for calculating the number of multiples between x divided by 2 and x of an arbitrary odd square-free divisor p sub I triple dot p sub L. Here, p sub I is the smallest prime factor and p sub L is the largest. Remember that the 2 minus pi of p sub L terms in the original expressions would be canceled when the two expressions are combined. The odd square-free integers we have generated from the divisor p sub I triple dot p sub L contain one more prime factor than the divisor. So, their Mobius function mu values have the opposite sign of the divisor p sub I triple dot p sub L. Therefore, their contribution to m of x is given by the term minus mu of p sub I triple dot p sub L times the above expression, which gives the last expression on this slide. Now we can combine the two previous relations to derive a new series for m of x. To write this series in a simple and neat equation, I used the symbolism in the original article. There, I represented a square-free divisor containing one or more primes by the term p sub I triple dot, and specified that the terms in the series are arranged in the order of increasing odd square-free divisors. On this slide is the new expression for m of x. Remember, pi is the prime counting function, and mu is the Mobius function, and that the negative sign in front of mu of p sub I triple dot accounts for the fact that the square-free integers generated by p sub I triple dot contain one more prime than it, and therefore have opposite sign for mu. For several weeks, I was stuck trying to find a way to simplify equation 2. A rather plodding approach I tried was not appealing. Then, after restudying papers by Apostle and Hall, a new equation to represent the series for m of x came to mind that gave a much neater and shorter derivation of the main formula. I refer to this equation in Corollary 1 of the next slide. It is easy to prove that equations 3 and 4 are equivalent. Note that in equation 4, when k is even, the terms are 0 because the numerator of the fractions become -1 plus 1, which equals 0. Also, if k is not square-free, mu of k equals 0. So this leaves us with only odd square-free divisors arranged from smallest to largest, as in equation 3. In equation 4, we have a new series for m of x. So what can we do with it? Honestly, I did not know what to do with this equation. But for some reason, I remembered this really cool limit equation for pi of x I saw while studying a textbook by Sierpinski. And it worked to simplify equation 4. Here is Sierpinski's relation I refer to as lemma 1. When x tends to infinity, the limit of pi of ax divided by pi of bx equals a divided by b, where a and b are positive real numbers. A is less than b. So let us recall the last equation for m of x, which is shown in equation 9 of this same slide. I'm going to use Sierpinski's relation to simplify this equation. I begin by dividing each side of equation 9 for m of x by pi of x. Then take the limit as x tends to infinity and apply Sierpinski's lemma. Notice this step reduces the terms on the right side of the original equation containing the pi of x function to a sum of odd rational fractions, because when k is even, the numerator of each term equals -1 plus 1 equals 0. Also, each term is square free, because otherwise the factor mu of k equals 0. After combining terms, we obtain the simplified sum in equation 10 at the bottom of the slide. It took some time before I realized the terms of the sum in equation 10 can be separated as shown in equation 11 on this slide. This would allow me to apply a theorem of Hall and Apostle shown in equation 12 to further simplify the equation. By rearranging Hall's equation with s equals 1, we can rewrite equation 11 as shown in equation 13. Adding the series within brackets and multiplying by 1/4 gives the new limit formula for m of x in equation 14. The infinite sum in equation 14 on the previous slide is a classical expression. Von Mango in 1897 and Landau in 1899 indirectly proved that the sum converges to 0. Vallée-Poussin, in his 1899 monograph, where he proved the prime number theorem, also proved a limit for the sum and a relation for its rate of convergence. Here is Vallée-Poussin's theorem. The sum mu of k divided by k tends to 0 when x tends to infinity, and its absolute value remains less than h divided by log x, where h equals a constant. Next, let us recall equation 14 of the previous slide and take the absolute values of the terms. Then, using Vallée-Poussin's theorem to substitute h divided by log x for the infinite sum in the equation, gives the main formula of the published article, that the limit m of x divided by pi of x equals the limit of h divided by log x equals 0. H equals a constant. So, how can we use this new formula? Recall, the title of this presentation is The Riemann Hypothesis, an idea whose time has come. I'm going to show how to use the equation to resolve Riemann's hypothesis. To resolve Riemann's hypothesis, we use the equation to evaluate a limit for Merton's function m of x given by Littlewood in 1912. So here's Littlewood's limit theorem for Riemann's hypothesis. Riemann's hypothesis is equivalent to the statement: for every epsilon greater than 0, the function m of x divided by x to the 1/2 plus epsilon approaches 0 as x tends to infinity. This statement can be expressed by the following limit. The limit of m of x divided by x to the 1/2 plus epsilon power equals 0 for every epsilon greater than 0. To use our limit equation to evaluate Littlewood's limit, we proceed by multiplying both sides of the equation by the limit of pi of x divided by x to the 1/2 plus epsilon power to obtain equation 16. Then, multiplying the right side of the equation by log x divided by log x, which equals 1, and using limit theorems, we can write equation 16 as shown in equation 17. Applying limit theorems again, equation 17 is written as shown in 18. This sets things up to use the prime number theorem to set the limit pi of x log x divided by x equal to 1. So now, using the prime number theorem and limit theorems again, we can simplify the expression on the right of equation 18 to give the equality shown in equation 19 on the next slide. Equation 19 makes one think that we are no better off than where we started. But there's a powerful tool we can use to evaluate this limit. We can apply L'Hopital's rule to the limit on the right and take the derivative of the functions in the numerator and denominator 2 times and obtain this simplified equation 20. According to Littlewood's criteria, the Riemann hypothesis is true if for every epsilon greater than 0, the limit on the right side equals 0. For epsilon equal 1/2, the factor 1/2 minus epsilon equals 1/2 minus 1/2 equals 0. So its product is 0. I will leave the case epsilon greater than 1/2 as an exercise for the viewer. However, for the range epsilon greater than 0 but less than 1/2, the exponent 1/2 minus epsilon of x would be positive. And any positive power of x, when x is greater than 1, tends to infinity as x tends to infinity. Therefore, the limit is infinite in this case. This result proves an exception to Littlewood's criteria, therefore proving the Riemann hypothesis is not true. Thank you for watching.